Okay, so today we are continuing our lectures on Bootstrap. And on Wednesday we talked about parametric Bootstrap. We said in parametric Bootstrap you are going to assume that your data comes from some mathematical parametric distribution that has, this mean, this standard deviation, or whatever it is. Okay, so you're going to assume that it comes from a normal distribution, or you're going to assume it comes from a whatever distribution. In non-parametric Bootstrap, we do not make these kinds of parametric assumptions about the population. Okay, instead we make a different big assumption. Okay, and the different big assumption is that our sample that we have is representative of the population. This might be a good thing, this might be a bad thing, okay? But you are going to assume that your sample is representative of the population, and therefore, if you want to create a sampling distribution, you can create a quote-unquote population, kind of a pseudo population, by taking your current sample and then just duplicating it like 1,000,000 times. Okay, so you're just going to take the current sample you have, you're going to clone it a whole bunch of times, and that's going to stand in for what the actual population is, because you are assuming that your random sample is representative of the population. Okay, and then you perform sampling on that population, and that will produce a sampling distribution. Once you have your sampling distribution, you can then answer questions for your hypothesis by comparing your observed sample to the sampling distribution and seeing how often would what does the sampling distribution say about how often my observed sample could happen by random chance. So again, instead of actually having to duplicate our population, or duplicate our sample, 1,000,000 times to create our population, we can just actually sample with replacement. We'll just resample our current sample with replacement, and that's equivalent to creating an infinite number of duplicates of my sample mathematically. Okay. So then, so that is the idea behind non-parametric Bootstrap. We'll look at a little bit of code demonstrating that, and then there's a package called Boot that does this for us quite nicely, and that's what you'll use in your homework. Okay, so so kind of our in-lecture example comes from our textbook. We're going to continue on with our Latino education achievement data set, which says that we are interested in seeing if there's a relationship between the mean education achievement level of immigrants from Mexico versus immigrants from other Latin American countries. Okay, and so that is what our data set looks like, and we're going to do Bootstrap to see if our data suggests that there is or is not any kind of relationship there. Okay, so we do just some summary statistics. We see that we have 30 in our data set. We have 150 people total. 34 are not from Mexico, and 116 are from Mexico. And the mean of those not from Mexico are 64.5, and the mean from Mexico is 58.6. So that's a difference of about 5.9 points. Okay, in this education achievement measure. Okay, and again, unfortunately, we don't actually know what education achievement level means, other than big numbers mean more education and lower numbers is less education. So we're not quite sure what these numbers actually mean, but what we have is a difference of 5.9 points, and we want to know, is this difference significantly different from 0, or could it be just a result of random chance? Okay, and so here our null hypothesis is that the mean education achievement level of immigrants from Mexico is equal to the mean education achievement level of other countries. or that the difference between those means is 0. And again, under our null hypothesis, this basically states that the sample of data that we have, the two samples, can be said to come from the same population. Okay? Both samples are coming from the same population. That's what the null hypothesis says. Okay? And so we will say, if the null hypothesis were true, what kind of differences might we observe just from random chance? And we'll say, is it possible to get this difference of 5.9 just from random chance? That's where we're going to build up a sampling distribution. Okay. So in parametric Bootstrap, what we did was we said, okay, let's draw our values from the normal distribution. We're going to assume our population is normal. We're going to draw values from there. In non-parametric Bootstrap, we are not going to say, let's assume normal. We're going to say, let's just resample our sample with replacement. Okay, that's effectively, again, taking our sample, making an infinite number of duplicates of it to create kind of our fake population, and then we draw from our fake population. So, so the code looks like this. Okay, it's really I've added comments to the code to kind of make it a little bit more complicated, but really the actual code is just this for loop with just maybe 3 lines of code inside. Outside I have, you know, set seed and create a vector to store our differences. And I mean, if I wanted to, I could even just kind of compress this down into 1 line. But we can see the bootstrap happening in these 2 lines here. What we do is we sample this column, Latino $achievement, okay, which is that vector of 150 values, and we're going to sample 116 values from that vector, but we sample with replacement. So that's equivalent to taking this vector of 150, creating infinitely many duplicates, and then drawing a sample of 116 out of that giant population C, okay? And then we do the same thing for the other group, okay? But that time we're only drawing 34, okay? And so this is saying that if the null hypothesis were true, both the values for Mexico and other are coming from the same population, okay? And so this is what kind of values we might see if the null hypothesis were true. We're just seeing what kind of differences can we get. And so, so we just take the mean of kind of our simulated Mexico values and the mean for our simulated other values, other country values, and we're going to take that difference and store them into this vector differences, diffs. Okay, so again, this is just what kind of differences might we observe from random sampling if the null hypothesis were true. If the null hypothesis were true, we're just drawing from the same population, and because it's random, we might get differences, but could we get a difference of 5.9? So I do this 10,000 times, and I say, okay, of those differences that I've observed, how many of them are greater than 5.9, greater than or equal to 5.9? And this turns out to happen about a little under 5% of the time, 0.0469, okay? You know, 4.7% of the time. So, so now we have to make a decision. We say, okay, this is my, excuse me, this is my empirical p-value, and so if my empirical p-value is, you know, around 4.7%, I have to make a judgment call, right? And so prior to doing our hypothesis test, we should have selected an alpha. We should have selected a significance level. And, you know, by default, alpha is frequently 5%, but maybe a smaller alpha is better. Who knows, okay? And so depending on your significance level, or basically how willing you are to make a type 1 error, you will decide whether this is a significant difference or not, okay? Are you, and so this is what we should, this is what we get, okay? So that's, this is basically the non-parametric bootstrap. If I pull up the notes for the parametric bootstrap, think this is. Okay. The code here is very similar, okay? Except, so if we look at this line of code here, we've got diffs, and this part is just mean for the Mexico values minus mean of the other values. That part is pretty much the same here. The only the difference that we have is how we are getting this thing. So with non-parametric, we sample our column of values with replacement, and with the parametric bootstrap, we aren't sampling any values. We're using R's normal value generator to generate new random normal values. Okay, so parametric says our values are coming from the random normal. Non-parametric says our values are coming from our actual data, but just duplicated. Is that okay? All right. Let me talk about PackageBoot. PackageBoot is a package for R that's useful for doing Bootstrap. You know, we're really only going to cover a little bit. You can look up more information online about things like Bootstrap confidence intervals and stuff like that. And we're not really gonna get into that in our class, but PackageBoot kind of does a lot of these utilities which are useful for us. Okay, for PackageBoot to work, you need to give it 3 arguments: the data that we're gonna resample, the statistic that's gonna be calculated, and this is a function that we have to define. So we have to define the function for how to calculate our statistic, and there's a very specific way to define this function. Okay, and then the number of replicates that we need to do. So like 5,000, 10,000, whatever it might be. Okay, you can give it other arguments, but they have default values. So really, these are just the 3 that you need to be sure to do. Okay, boot. The function boot, which is kind of the central function that powers the library boot, does something a little bit clever in the way it does its bootstrap resampling. Okay, instead of actually resampling the data values themselves, what the function boot does is it resamples the indices of the data. Okay. So if we look back to our implementation of the non-parametric bootstrap, what we did was we took Latino $achieve. We took that actual column of 150 values and we drew samples from it. Okay, what the function boot does is it's going to take your data, Latino education, and it's going to say, oh, there's 150 rows in it, and so what it will do is it will resample the vector 1 through 150 with replacement. Okay, so it's going to say like I've randomly selected row 37, I've selected row 15 and row 2, and some of those values will get selected more than once, and some won't get selected at all because you are resampling with replacement. Okay, and then boot will then take that and then subset the original data using the resampled indices. Okay, and that's going to kind of produce a new bootstrapped sample. All right, and the reason why we might do this is that this allows us to use multiple columns of data with multiple columns or multiple variables from our data set. So, so for example, if you want to calculate the correlation between 2 columns, okay, it would not work if you take one column, draw a bunch of values with replacement from one column, and then separately go to the other column and draw values with replacement from the other column, because that's going to break any kind of association between them. So what boot will do is it will say, okay, these columns go together, and we are going to just resample. We're going to select row 2 and row 15 and row 28, and you're going to select both values from row 2. You're going to select both values from row 15 and both values from row 28. And so if there is correlation that exists between the two columns, that will be maintained when you do your resampling. Okay? So the function boot resamples the indices of the rows of the data rather than each column independently or something. Okay? Which is what we did over here, which works fine when you have only one column that you're working with. Okay, but if you're gonna have to deal with more than one column, you're gonna want to sample the row indices yourself. Okay, or use PackageBoot. Okay, and so the important thing when using boot is being able to write this function to determine the statistic that needs to be calculated. Okay, and so so in our case, we want to figure out the mean achievement level of 116 Mexican immigrants versus mean education achievement of 34 immigrants from other Latino countries, and we're going to calculate that difference. That's the statistic we're trying to go for. Okay, when we write our function, this statistic function, it's always going to be a function of two things: the data and the index. Okay. When we call FunctionBoot, we specify the data, the statistic function, and the number of replicates. And then what boot will then do when it runs is it will pass the data to this function, and it will pass the bootstrapped index to the statistics function. Okay, so when you call boot and you provide it to this function, diff_func, it's going to pass these two things to it, and this will return the values. Okay, and so here I've written my function as a function of the data and the index, and the very first thing I do is I subset my data according to the indices. Okay, so I say take, so in our case we're going to take our Latino education data set, okay, which starts off with 150 rows, and I'm going to subset it to basically 150 rows that were selected at random with replacement from the original thing. So this will mean my new data set after I subset will be something like, it's going to be like row 6 and row 15 and row 28, and it's going to be 150 rows, but they've been selected with replacement. So some rows are going to be selected more than once, and other rows will not be selected at all. Okay, and so that's going to be the first thing that we do in our function, is we subset the data according to our indices, and from there I calculate, I extract 116 values from the achievement column to kind of be our sample for immigrants from Mexico, and then I'm going to take the remaining 34, and that's going to be our sample other, and we're going to calculate the mean difference between these two groups. Okay, so the function, the last line in a function, if you don't explicitly write return, then the last value in the function that gets calculated is going to be the value that gets returned. So it's going to return the difference between mean Mexico and mean other, and this is done by subsetting our data using the index that boot has done. Okay, so this part is basically the bootstrap resample. Okay, because function boot will pass, will give the resampled indexes here. Okay, and then now we just need an arbitrary way to say I need 116 values for here and 34 values to go in here. Is that okay? How this function is working? And so therefore, when you run the function boot, you're going to say boot data is equal to, we have our Latino education data set stored in object Latino, and then the statistic is this function that we've written here, okay? And so what boot will do is it's going to say, okay, it's going to pass the data into this thing and pass the resampled indices here, and we're going to say run this 10,000 times, and we store the results into this object called boot results, okay? Or whatever object you want. Okay, so when I do this, if we look at boot results is going to be I guess I did, I ran this on my computer and I did this 50,000 times rather than 10,000 times. And if we ask for the structure of boot results, it's a big list, okay? Boot results is a big list. It's a list of 11 things. It kind of starts off, and when I did it 50,000 times, okay? And it's going to store basically 50,000 values returned by this function that I've specified, okay? And so I can take a look, and that's stored in this list $T, okay? It actually stores the entire data set itself in here, and then it also gives us kind of some seeds and all of this stuff, and you can look at like what does, if you ask for the help on boot, it specifies all of these arguments that you can give it, and then all of these values here. So it'll tell you, if you want to know how did it select these things, you can use the value of random seed when boot started to work and things like that. Okay, so it stores all of this in here, and then if you wanted to, you can then there's other functions like find the confidence intervals and stuff like that. Okay, but anyway, we can just take a look at boot results $T. Okay, and these are kind of the different values I observed. We can see it's centered at 0, as I would expect, because this is what's generated under the null hypothesis, right? Here's a kind of a density plot, and we also see it's centered at 0, as we would expect, because under the null hypothesis, the values for our 116 immigrants from Mexico and the values for our 34 immigrants from other countries, they are coming from the same population, and so when I calculate the difference between this mean and that mean, I would expect to get a difference of 0, okay? And that's what this says we get under the null hypothesis. So this is our distribution of kind of values that we see under the null hypothesis, which is centered at 0, exactly as I would expect. So my mean ends up being, the mean for whatever reason is a little bit higher than 0, but yeah, centered around 0. And the standard deviation is around 2.9. And if we calculate the p-value, how often were any of our results larger than or equal to our observed difference, this happened about, again, a little bit under 5% of the time, around 4.3% of the time, which kind of lines up with our other results as well. Okay, and again, just like before, you would then have to make a judgment call as to whether this is a significant difference or not. Okay. Let me open our homework assignment. Okay, your homework. This last homework assignment, and I just kind of want to talk a little bit about some of the Bootstrap stuff that you will see there, okay? One of the examples that I use, I have this worked example up here that uses this Law82 data set, okay? The Law82 data set comes from this package called Bootstrap, which has its own Bootstrap functions, but we don't actually use them. We're only using PackageBootstrap just to get its data, okay? And here's this is an example of why we might want to use PackageBoot to do this, because here we're calculating the correlation between these two variables, okay? And so if we ask what this data set law 82 is, okay, it says we are looking at data from 82 law schools in the United States, okay? And then we have data frame law, which is a random sample of 15 drawn from the universe of 82. So I don't know how many law schools there are in the United States, but apparently, for the sake of this thing, we're saying there's a total of 82, and that's it, okay? I think there's probably more, but we're gonna just say there's only 82, and this is the entire thing. And we're looking at, you know, kind of scores on LSAT and scores on GPA, and I don't know anything about law school or the LSAT. Is anyone planning on entering law school? No, maybe, okay. And anyway, so this, I'm assuming, is admissions information, and this was from 1993, and so these GPAs seem quite low, but I don't know. Okay, so, you know, one law school, their average LSAT score was 6.22, or 622, and their GPA was 3.23, and so on and so forth, and we can create a plot of this. Law 82, all right, and so this is kind of the correlation, and we can see, yeah, in general, schools that had higher average LSAT scores had higher average GPAs and things like that. And we can ask, okay, what's the correlation between these two values? Okay, and so in the population, the correlation is around 0.76, okay? And what we have, the idea of Bootstrap is we're gonna just select 15 schools out of here, okay? And so I guess I could do points. Undefined. Oh. Okay, and so apparently these are the 15 that were randomly selected, but you know, somebody else could have selected 15 at random from the 82 and gotten something different, okay? And so that's kind of what I explored over here. I just said, well, okay, we observed a sample in our 15, our correlation was 0.776. If somebody else took a random sample from the 82, they might get a different correlation. Here we get a correlation of 0.95. Someone else takes a random sample, they get a correlation of only 0.63. And if someone else takes a random sample, they get a correlation of 0.817, okay? But we'll just do Bootstrap, and I'm gonna go ahead and skip down to using PackageBoot. And what we're gonna do is we're gonna take our sample of 15 law schools, and we're gonna resample that sample with replacement, okay? Because we're gonna hope that I can take my sample of 15, duplicate it a bunch of times, and now this is kind of like having the sample of the universe of 82 law schools or something. So it's a little bit dangerous again, but that's the best we can do with the data that we have. So here again, we're going to just kind of take our sample of 15. We're going to get a set of indices, which is going to be the values 1 through 15 sampled with replacement. So if it's like, here's the values 1 through 15, and I'm going to say sample 1 through 15. I want, I think I just say sample 15, replace equals true. Okay, and so we can see, you know, when I sample the values 1 through 15 with replacement, here I got the value 13 3 times, the value 7 shows up twice, you know, the value 2 and the value 3 doesn't show up at all. We're just resampling our sample, and if I did this again, you know, something else happens. So some certain values get sampled more than once, other values don't get sampled at all. And that's basically, boot is going to pass this index over here to kind of subset our law school data. So here is, you know, our 15 rows, and we're going to just kind of sample these rows accordingly, okay? And so when we do that, we can then calculate the correlation between the LSAT and GPA by just extracting out the LSAT and the GPA columns and calculating the correlation between them, and that's a correlation function. You know, if you're into just writing only a couple lines of code, this can be compressed down into basically one line, okay? And then we would call Bootstrap by saying take boot. Our data is this data set of 15 schools, and for each replication, calculate the correlation function. Okay, so I'll go ahead and I'll run this, and then we'll go ahead and run this. And here we get a bunch of stuff, and what we want to do is we want to get an estimate of the standard error. And here it says, you know, we're estimating our standard error to be around 0.1377, okay? But again, if we did this on any of the other 15 samples, we can see that our standard errors vary quite a bit, okay? And so this is just kind of an indication that depending on what your sample looks like, it can lead to kind of different conclusions about what the population looks like, okay? In that, you know, your sample, again, the big assumption of Bootstrap is that the random sample you have is representative of the population, and therefore to make our population we're just going to duplicate our random sample a bunch of times. If your random sample is not representative of the population, you're going to run into trouble. But the problem is you have no way to tell, okay? It's just a random sample. You have no idea if it really is representative of the population or if it's not, and you're just kind of hoping that it is. But again, we have no way to tell. So that's kind of you know, a cautionary tale behind Bootstrap. It's a useful thing, but there are limitations. I want to talk a little bit about this last task in your homework, okay? And this comes from Simon Newcombs Experiment back in the 1880s, okay? And so this was a long time ago, and they were trying to figure out the speed of light. And you know, they had limited technology in 1880, okay? They didn't have lasers, they didn't have stopwatches that could measure time in nanoseconds or anything like that, and yet their measurements come in at nanoseconds. They're trying to figure out how long it took light to go from their office in the, I guess, the Naval Academy Observatory to reach the Washington Monument. So they're over in kind of DC, Washington, DC, which is about 3.7 kilometers away. And so, you know, they shine a light, it bounces off of a mirror 3.7 kilometers away, and it comes back, and they're trying to time how long it took, okay? And so in order to do this, because nobody has this, like, nobody's reactions are within microseconds or nanoseconds, they have a rather creative solution, okay? And so if you click this link, this is it's worth looking up these things on YouTube, okay? This is kind of the little diagram here. So we have Newcomb and Michelson, and most of these things will show up under kind of Michelson's name, but what they have here is this mirror that rotates, and maybe kind of the idea. I'm going to go ahead and go to YouTube and show you. Okay, so the idea is there's this mirror. Here's this mirror with a bunch of sides on it, okay? And and they know the speed of how fast this mirror is rotating, okay? And then they shine light, okay? It bounces off the mirror, it comes down to the other side of the river, and if the rotation of the mirror is correct, it's going to bounce off here, hit the mirror, you know, here it says 35, but you know, far away, comes back, and then we can see it, okay? But if the rotation is off, so if the rotation is correct, it works. Where is the diagram where the rotation is off, okay? But if the rotation is off, it's going to bounce off, and because this thing is at the wrong angle, it's not going to kind of go into the receptor. So by knowing how fast their little mirror is spinning, okay, and whether or not the light is bouncing off, and the timing of the light that goes, you know, basically a 7.5 kilometer trip and back, they could figure out the speed of light, which I think is a rather ingenious method based on the limited technology that they had, okay? Nobody had super accurate stopwatches or anything like that. They're able to measure how fast their mirror is rotating, and based on knowing kind of what angles are necessary, okay? So they had to know their trigonometry and all of that. What angles are necessary and how fast that goes, they could figure out the speed of light. So anyway, they did all of these measurements, okay? And they got pretty good results, okay? Their estimates were 299,860 kilometers per second or 299,810 kilometers per second versus the modern accepted value of 299,792, okay? So 299,792.93, that's kind of the accepted value today, and they estimated 299,860. So they were off by, you know, 70 kilometers per second compared to the speed of light. That's pretty good, okay? But anyway, we want to know if this came in any good, and so we have these values that measure kind of the time that it took, which is around 24,800 something nanoseconds, okay? And these are kind of these values, and the true value should be 24,833 nanoseconds. So the mean values should be 33, and we get a mean of around 26.2. Okay, and so we want to know if the null hypothesis were true, could a random sample produce a value as low as 26.2? Okay, and so in order to kind of create our sampling distribution, if the null hypothesis were true, is you are going to take this vector of data and recenter it so that its mean is 33. Okay, and so that's going to kind of simulate what kind of values you might get if the null hypothesis were true, where the mean is 33, and then and basically what we are saying is that our sample of data is representative of the kind of deviations from the mean that we might see. So, so we're going to center our data at 33, and we're going to say, based on kind of the variance that we see in our data, could a population centered at 33 still produce a mean of 26.2? Based on the variation I see in my numbers, could a population centered at 33 produce a mean of 26.2? And that's how you will conduct your Bootstrap test. Okay, you might need to do a whole bunch of these things, and you're going to get a pretty small p-value, indicating that based on our observations, you know, it's quite unlikely that if the true population is at 33, that we would get values with the average of 26.2. So that indicates that despite Newcomb and Michelson's best efforts, you know, there's probably something just a little bit systematically wrong that's getting their mean value to be off. Okay, but you know, we still look back, and I think everyone acknowledges that these were very significant improvements in our understanding of the speed of light. So this is like way before Einstein and special relativity and things like that. But they recognized that light was not an instantaneous thing, that there was a speed to it, and they were able to record its speed to quite a good deal of accuracy there. Okay, so anyway, you'll do a bootstrap there, and then you'll redo it again after removing the outliers. Okay, so it's week 9 Friday, and this pretty much concludes, I think, all of the main content for the course that I want to cover. In 10th week, next week, I'll talk about the final exam on Monday, and then on Wednesday and Friday, I got some additional topics that I think are interesting and kind of fun. I won't test you on those, but I think I don't know, I think they're neat. So come and do that. Instructor evaluations are out, and so my request is that you fill them out. And I told the other class this, so I'll tell you the same thing. I will give 1 percentage point of extra credit to everyone's final grade, but the way it's going to work is the entire class needs to have a participation or a response rate of 70%, okay? So if the entire class achieves this response rate of 70%, then everyone will get their 1 percentage point of extra credit, or no one will get it, okay? If you guys come in at 50% or 60 whatever percent response rate, then nobody gets the extra credit point. So it's kind of as a whole, the entire class, I want to see a 70% response rate, and that will give you a one percentage point of extra credit. Okay, we'll end there. Have a good weekend. We'll see you guys on Monday.